Alright, we're going to start by watching this video. Make sure you write something down on your note-taking guide. And the first thing we're going to write is the title. So ignore the ad. Here's the title, the Galton Board. So write that down on your note-taking guide. And then any of those empty parts of the organizer you can fill in after as you watch the video, okay?
My name is Lloyd. Today we're going to talk about the Galton Board. Invented, or at least named after Francis Galton. What we have is a bunch of pegs and a bunch of slots. Now when I turn this over, all of these balls, 3,000 of them, will fall through those pegs and they'll scatter randomly, in the sense that we don't know where each individual ball will go. But because there are so many of them, how do we know this? Look at all that wonderful wild randomness turning into pretty much the same exact shape every single time. A normal distribution. Let's begin by talking about the pegs. The pegs on my Galton board are arranged in a triangular pattern like this. We start with one peg. Below that peg in the second row, there are two pegs on either side. The third row contains pegs arranged like this. The fourth like this. And so on. Now, because of this arrangement of pegs, the Galton board is sometimes called a quincunx. A quincunx is a pattern of 5 objects, a certain way of arranging them, where 4 of the objects are on the corner of the square, and the 5th is in the middle. You're probably familiar with a quincunx if you've ever looked at a die before. Now, anyway, when the balls fall through the machine, they first reach peg number 1 in the first row. And once they do that, they have a choice. Well, they don't really have a choice, but they will either go left or right. And because of the way the Galton board is designed, there's about a 50-50 chance that any given ball will go to the left or to the right. Once that's happened, they've reached the second row of pegs, where they will either go left or right. Left or right. Now, because at each peg a left or right bounce is equally likely, in the long run, across a large number of trials, we expect balls whose complete paths contain about the same number of left and right turns to be the most common, which means we expect more balls to wind up pretty much right below where they started, and many fewer on the edges, which corresponds to having way more of one kind of bounce than the other. We don't know where any individual ball will wind up, but we can say something about how they will all behave. Now, the actual...
All right. Everything past this is above what we're learning. We're just learning about how it naturally, the balls fall in that Galton board, okay? All right. Anybody need more time to write something down? Good. The word that was a new word here was
Pegs.
pegs. Nobody knows what pegs are?
No.
Have you ever been to the carnival where you drop the coin and
No. Like Andrew will go get that pegs. I just so funny.
like you try to land it in like one of the slots at the bottom so you can get a prize? No?
What is the word? Like,
You showed it right here.
The Galton board is sometimes called
like,
There you go.
that,
The shape.
what's that thing?
It's a bell shape.
Like it's a,
Bell curve, right?
You talking about the parabola?
yeah.
A quincunx is a pattern of 5 objects, a certain way of arranging them, where 4 of the objects...
Parabola. Okay, get a pencil. Okay, so in our notes it says when the histogram, but of course it can be a dot plot or anything, any data display. So when it has that bell shape, the distribution can often be modeled by a normal curve. Normal which is a bell-shaped continuous function. Alright. So a sketch would be that bell shape. It gets very, very close here at the bottom on the left. And then it increases at the top is the highest and then back to low values. Okay? So this is a normal curve. So if this is normal, what's not normal?
Something that deviates from this one.
Yeah, do you remember the word skew?
Oh, yeah, the right skew. the left
Right skew and left skew are not normal because the data skews to one side more than the other, right? So when you have a normal curve, it has no skewness. Everything is normally distributed and it's pretty. Okay. All right, everybody have the sketch there. Okay, we're gonna go into depth into what the normal curve holds inside. So the properties of a normal curve make it useful to model for data distributions. And so these distributions, the percentages, they fall within intervals. What do you think of when you hear the word interval? What does it mean? Without using the word interval, what does it mean?
Like every certain amount of something happens.
Yeah, so like sections, cycles, like from here to here, boundaries, right? That's what an interval is. From 3 to 7. Remember when you answered the question about the Netflix problem? That's where I got 3 to 7. When the average was 5 hours, and then you added 2 and subtracted 2. What was the average number of Netflix hours the students were watching?
5.
What was the interval? 5 minus 2 is how much?
3.
3. So between 3 hours and 7 hours, because 5 plus 2 is 7. If you did that worksheet, you know what I'm talking about. Okay, so those intervals in the normal curve are determined by the mean, which was 5, right, for the Netflix problem? Remember? It was 5. And then the standard deviation was how much? What was the standard deviation on the Netflix problem? I just said it. What was the square root of 4? 2. So the mean was 5, the standard deviation was 2. We did 5 plus 2 and 5 minus 2, which gave us an interval of 3 hours and 7 hours. Okay. But now we're looking at it more in the normal curve. So it's going to be very helpful. Alright, can I go forward? Yes? Good. Alright, here's our 3 intervals. The first interval is approximately 68% of the data. Okay? So this section of the curve, under the curve, is 68% of the data. Approximately. Okay? If you didn't know this symbol, write it down. This is approximately. I'm going to abbreviate. Okay?
So then,
Tilde, there you go. Yes. When we use that in math, it means approximately, not exactly. Okay? Because you know exact, not everything is exact. There's margin of error. The what? Oh yeah. That's actually the answer to the next part. This is one standard deviation from the mean. Okay. Did this one show up on your notes? Yeah, the little bracket.
Yeah.
Okay, so here in under the curve, if the total part highlighted is 68, how much is each side?
1. Out of 10.
34.
Wow.
34. Okay.
Yeah.
Yeah, each one is 34. From the mean, 34% is that first deviation. We just split it in half, right? 34 plus 34 is 68. Good job. Okay, next one. The next one is we start adding more. So if this was 68, Now this one is 95%, approximately 90% of your data values are in those first two deviations from the mean. Okay, write it down. So if you're wondering what part did we add, I need you to use your highlighter and highlight any color. This is the second deviation we added from the original first deviation. Okay? Now, in order for us to calculate how much is each of those sections, first we need to know how much more percentage did I add from 68 to 95. How much more? How much? Sorry, yes.
27.
27. Does everybody see that? So do this side work here. 68 plus how much? Gives me 95. 27. Okay. Now this is 95 approximately. But if I want to know how much is each one of these intervals, what do I need to do? Divide 27 by 2 is how much? How much? 13.5. All right, anybody confused for the 13.5? Confused. So you see how here we did half of 68 was 34 each? So we already have that part here. This is 68. So then the total here is 95. So how much did I add to 68? 27. So now I can split up 27 into two parts. It's 13.5. So half of 27 is 13.5. Because together, if you add these two, it should equal 95. Okay. All right. Last one.
100%.
Well, not exactly. They actually only do approximately 99.7. Very close to 100 though.
Why not 99.9? Because, I mean, it could be more than 3.
Right. Yeah. So that's 3 deviations from the mean. Okay. By the way, where is the mean on this curve? Right in the middle. Yeah, right here.
Yeah.
Okay. So with your highlighter, that's going to be very small portion. So since I went ahead and highlighted everything like past the second deviation, what is 100 minus 95?
5.
5. So what's half 5?
2.5.
So this is of the data. Okay. Now yes, it should equal 100, and I'll show you that on the next one because the next one gives us more space to do that. Okay. All right. Turn your page once you're done. Okay. So you might be wondering, when are we ever going to use this? This normal curve is used for many naturally occurring phenomena. Okay, so this is including but not limited to stuff that happens naturally, okay? Like the heights of people in the city. Okay? Can people without surgery control how tall they are?
No.
No. What about how much you weigh when you're born? No, that just happens. Test scores. Now that I get debate on because people say I can study and get a higher test score and whatever. Yeah, that's true. But naturally, if you didn't know, there's people that have higher IQs than others. That's just natural. And we can't control that. Okay? Someone in the room will always be smarter than you, I promise. Okay?
What about the smart person?
Yeah. Like there's just natural born geniuses. Did you know that?
Or under that.
So yeah, that happens. Average daily rainfall. Can we control how much rainfall? Like rain, stop right now.
Yeah.
We can't.
Now, you know, there's like in Dubai or whatever, it didn't have rain, they like send salt into the air and stuff so that it would rain. So,
But without that, can they control it? Can they control that they get no rain? No. So, shoe size. We'll talk about shoe size at the end, okay? Tossing a coin, rolling a die, that's just up to chance, right?
yeah.
Okay. So that's something that happens naturally. Yeah.
You can actually change it.
You can what?
You can change it.
Yeah, you can. That's why I said without surgery, can you
No, what if I
decide your
get
height?
those little protein shakes that make me grow because your iPhone?
Alright. So that leads us to the empirical rule. This is the rule you're going to use for your yellow paper. Another word for this rule is the 68, 95, 99.7 rule. So when you see those three numbers, they're talking about this rule, okay? The empirical rule. Alright, we're going to use 4 colors of highlighters here. So someone tell me. 4? Yeah. First color, right here, right down in the middle. What percentage is that?
1, 5, 6, 5 plus 1. No, 5 plus 45. 5 times 7.
It's at the center.
0, 1.
50. 50.
100%.
50% of the data is right in the middle because the whole is 100. And then someone else said this is the mean. If there's a question that says, what percentage of the data, what is the average 50% of the data? Where would you look?
The middle.
The middle, because that's where it splits it in half, right? Okay. Okay, next color. Switch color. Any color doesn't matter as long as you keep it the same on both sides. Okay. 1 deviation from the mean is how much percent of the data? 1 deviation. Look back on the left side. What percent of data is 1 deviation from the mean? 68. 48. Yeah, now if I want to look at lower bound and upper bound and you split it, then that's 34% on either side. Okay. Alright, next color. Sorry, before we keep going, when we do these calculations, like we did for the Netflix problem, we add it from the mean. We do the lower bound when you do minus 1 deviation and plus 1. Right? Don't forget that. That's actually the calculation we're going to be doing after that. Okay, now we can do the next one. So again, when you're calculating the intervals, if I ask you what is the average rainfall 1 deviation from the mean? We do the mean plus 1 deviation and the mean minus 1. Then next interval, 2 deviations. 2 deviations from the mean. Deviations from the mean is how much percent of the data? 95, good. Okay. And so if they ask us 2 deviations from the mean, it's no longer +1, now it's how much? +2 deviations, standard deviations, and -2 standard deviations. I would just multiply it that way it's faster. Instead of writing the number twice. Okay. And then what was the percentage in these intervals? 13.5. And alright, that is 2 standard deviations from the mean. What's next? 3. Good. 3 deviations from the mean. And now it is not 95%, it's 99.7% of data.
Actually, I'll just more money. Less.
Okay, so here at the 3rd standard deviation from the mean, you will do +3 times the standard deviation and minus. This is, everybody knows this is SD, right? Standard deviation. It's not a 50. Yes. Yeah, we start multiplying because 1 doesn't do anything. You just add it and subtract it. I mean, unless you want to write the number twice, I wouldn't. 3 times. Great. Now, what was when we did the first one, we did -100, right? But if we actually calculate the distance from 95 to 99.7, how much more did we have?
4.7.
4.7. So we added 4.7, right? And then what's half of each? What's each of each?
2.7.
What's half of 4.7? 35. Thank you. Because from 95 to get to 99.7, we added 4.7. And half of 4.7 is 2.35 on each side. Okay? And then so what's left? Because we only did 99.7. What's left to get to 100? 0.3. So what is this small portion here? It is 0.3 together. How much should we need? 15. Good job. What's half of 30? So we're that far away. Now we got the full 100, right? If we sat there and added all these percentages, we would get how much? Okay. Alright, good job. Let's glue this on page 21.
21.
Okay, so now that we know the empirical rule that you have in your notebook, like I said, take it home if you need it so you can complete this paper. Okay. This is an example of a histogram for birth weight of newborns.
I thought baby was 8 pounds.
Yeah, the UK does measurements in kilograms.
Oh yeah.
So how much is 4K?
8 pounds.
Round about.
Probably. But what I noticed that they give me here is this N is the total number of newborns in the study, right here. And then they already gave me the mean, and they already gave me standard deviation. So, we have everything to calculate what they asked me for, okay? First question says, what do you notice about the histogram and the relationship to the normal curve that they drew on there? Okay. So even though it's not a perfect, obviously, curve, it's a histogram, obviously, it has edges. But what do you notice? It has the same shape as the normal curve, right? Approximately, roughly. What else? Same shape. What else? No, compared to the normal curve, not the curve.
It's more concentrated in the left. Is it the bin weight or whatever you know?
The bin height. What about the bin height?
It's smell. Yeah, it looks like.
Very big. Very big.
No, it's not. It's small.
In what areas does the height go above the curve?
Like 3.5.
Where the mean is, right?
Yes.
It's a little higher. And where else? Where else? At the beginning of the curve. Between what interval?
1 and 2.
Yeah, right before 2. The bars are higher. So you can write something down along those lines. Number 2. Number 2. Since there are 3,226 newborns represented in this data that are approximately normal, so this gives me the freedom to know that I'm going to use the bell curve, normal curve, and the empirical rule. About how many newborns from the study would you expect to have birth weights within 1 standard deviation of the mean? Exactly, what is it asking? How many what?
How many newborn from the study would you expect to have birth weights between 1 standard deviation of the mean?
Good, so let's use our empirical rule. How many percentage of the newborns are in that first deviation? We wrote it down. What's the percent for the first interval?
68.
68. So how do you calculate 68% of 3,226 newborns?
0.68 times 8,000.
Good. Okay, somebody go calculate that for us, please. And don't be trying to do it in your head, fifth grade. Who's calculating it?
Andrew.
Notice I'm gonna put approximately because you gotta have a whole number, so we're gonna round. What is it?
2,193.68.
Okay, we gotta round.
Keep tight.
You can't have 0.68 of a newborn.
2,193.7. 0.7.
Can't have nothing. It's a baby.
Oh, wait,
You can't have
Not
anything
that.
of a newborn.
2,194.
Is that rounding up or down?
That's 68%. Rounding up.
We gotta round down.
Why?
We need a full.
Hold on, miss.
What? So 2,190.
Miss,
Okay.
don't.
Why do we have to? Why can't it be more?
Because it's not a full. It's not a full.
Oh, we can't have a baby.
Yeah. Okay, so this is how many babies are gonna be in that first deviation. Now we need to know what the birth weights are in that first deviation. So how are we gonna calculate that? Do you know? What did we do here? We're looking at this part. How do we calculate that interval? plus 1 deviation and minus. Plus and minus from what number? Mean. So go back to the paper. What does it mean? 3.39. 39 minus 1 deviation, which is how much? 0.5. Okay, and then if we do the lower bound, we gotta do the upper bound. So it's not minus, what is it?
Plus.
Up. Plus 1 standard deviation from the mean. Okay, and then now we have our interval, and then we'll write a sentence about it. So let's calculate the lower bound and the upper bound of the interval and write a statement for these 68% of newborns.
So don't do it in my head.
Do not do this in your head, no. Please type it, somebody.
I'm so proud of you.
Do we have a number?
No.
Andrew doesn't have to be the only one to measure.
Like the only one with this computer. She's not ours.
It's 2.84 for minus.
And then how do we measure these weights? Kilograms.
3.94 for plus. Yeah, we could have done that in our head, right?
Maybe.
That's a lot of numbers.
So, alright, here's our interval. When you take these free response, remember you can't just show work, you gotta put it together and work. So, about, how many did we say was 68%? About 2,193 newborns. I'm going to abbreviate NB. Okay. Would have a birth weight between NB is newborn.
Do they weigh every baby?
Between what? 2.84 kilograms. Good. And 3 point. Because that's not a seat for you. That's my table. So you got paid price. This is where I stand. Okay. So. Make sense?
Just answer it. Just answer it.
Yo, who is calling?
I'm trying to do my job. Anyway, so the next question, what does it say? 2 standard deviation. So when we do this calculation, you're going to change the 1 to a what? 2, and so forth, okay? This is due on Monday.